Okay, folks, I have a little bonus video for you here. The title is Technique to Analyze Seemingly Crazy Complex Numbers in WebAssign. And I came up with this when my good friend Owen and I were talking during a 7-8 period today, when I was trying to give him a different strategy than the one I'd shown in previous videos, and this is what we came up with. So I showed this to a couple of people and they said, hey, this is awesome, you really need to teach it this way in the future. So let's see what I'm referring to. So what students struggle with is figuring out what the complex form of this, what the polar form of this complex number is. In order to do that, you have to find the modulus of z and the argument of z and that kind of stuff. And in this form it's difficult to do. But what if we factored out a 6 from this complex number? If I factor out a 6 from this complex number, then I'm going to have a remaining factor here of -1/2. And then I'm going to have a remaining factor here of I times √3/2. And let's just think about the distributive property for a second, make sure this is right. 6 times -1/2 is -6/2. 6 times I√3/2 is 6I√3/2. Okay, so now why did I do it like this? The reason why I did it like this is 6 is a multiplier, and this stuff in here, -1/2 plus I times √3/2, those are unit circle values. And because those are unit circle values, the radius of that circle is 1. So from that I can make the following statements. The modulus of z is equal to 6. Why 6? Because it's this multiplier of 6 times a unit circle of 1. That would give me a radius of 6. Now what about the angle? What about the argument, theta? Well, in terms of the argument, I need to think about my unit circle values. I have a real component of -1/2. I have an imaginary component of √3/2. If we're thinking about the xy plane, that's analogous to an x coordinate of -1/2 and a y coordinate of positive √3/2. That sounds an awful lot like the angle 2π/3. So there is your modulus and your principal argument, all from just doing a little factoring and thinking about what we know in the unit circle. Let's take a look at this next example here. 3√2 plus 3i√2. So I'm going to start with the same strategy I did before. I'm going to factor out a 3. That leaves me with √2 plus i√2. And unfortunately right here, the radius of the circle that these points would be on is not 1. In order to get it equal to 1, think of values on the unit circle that have √2 in them. The ones that come to mind for me are √2/2 and then √2/2. Unfortunately, I got to do a little work with right here, with this spot right here. I can't just put a 3 here because I divided everything in here by 2. In order for this to be equal to what I had over here, I better somehow multiply by 2. If I divide by 2, I better have a factor of multiplying by 2 to make sure it's equal. So if I do 3 times 2, that would give me 6. So let's just think about the distributive property and make sure that what we have here is equivalent to our original statement. If I do 6 times √2/2, that's 6 divided by 2, which is 3, times √2. Hey, that's the same thing we had here. That's awesome. Same thing would happen if I do 6 times I√2/2. We'd get 3i√2. So what can I do with this? From this, I know the argument of the modulus of the real number or complex number is 6. And the principal argument is whatever angle has a real component of √2/2 and an imaginary component of √2/2. That's π/4, folks. π/4. And I know you'll see numbers like this in WebAssign that have something like this and something like this. So what I'm trying to do is make a connection back to the unit circle for you. Well, let's look at another one, see if we can make another connection to the unit circle. What if I have z equals negative 12i? Well, I can write this as the complex number z minus 12i. Okay? And from here, I don't have a GCF, but I am going to factor out number 12. And let's see if this works. 12 times 0, still 0. 12 times negative I, negative 12i. What does this do for us? Well, it tells us that the modulus of this complex number is 12. And let's think about this. I have 0 on the real axis and negative 1 on the imaginary axis. That's like the point 0 comma negative 1 on our unit circle. And that occurs at 3 pi over 2. But that would be a mistake, because that's not the, well, it's not a mistake, it's just not the principal argument. Remember, our principal argument has to be between negative pi up to and including pi. So for this, I'm going to call that negative pi over 2 instead of 3 pi over 2. Still making a connection back to our unit circle. Okay, how about one where we have a complex number that really, it only has a real component, negative 2. Well, let me write that as negative 2 plus 0i. If I factor out a 2, and whatever you factor out, you always want to be positive because our modulus is always positive. Factor out a 2, that's going to give me negative 1 plus 0i. So I have, let's just check by the distributive property, that's going to be negative 2 plus 0i. So from this I know my modulus is 2. And how about our argument? Well, where on the unit circle do we have an x-coordinate of negative 1 and a y-coordinate of 0? Oh, that happens at pi. Perfect. Let's move on. One more crazy example for you folks. Unfortunately with this one, not only do I not see anything I can factor, but I don't see anything that looks like a value from the unit circle. So folks, I apologize, but this one you're really stuck to looking at what does this thing look like when I draw a picture of it. I have remember, this is our real axis and this is our imaginary axis. I have a real component of negative 3. I have an imaginary component of 2i. So this one, folks, you have to go back to the geometry. So my modulus is going to be equal to the square root of negative 3 squared plus 2 squared. It's going to be 9 plus 4, which is 13. Square root of 13. There's your modulus. Now for theta, well, hold on a second. Let's see. This is the angle theta that I need. But I'm in quadrant 2. If I use arctan of 2 over negative 3, I'm going to get something down here in quadrant 4. You have a choice, folks, and I talked about this in class today. What I would do here is one of two things. You can either do pi plus inverse tangent of 2 over negative 3, or you can do pi minus inverse tangent of 2/3. And I'm going to let you sort out why each of those works for this picture. And remember, so our modulus is root 13, and our principal argument is pi minus inverse tangent of 2/3. Okay, folks, a couple extra examples for you. I hope you find this useful.